this since it didn't record it earlier. So you can see on there, it's quite well done until we get to Thursday. And then it looks like I'm probably going to be teaching live instead of having a video. Then Friday, we'll review for Monday's quiz. Easy enough. A lot of the times, you know, when you look at this Monday thing up here at the top of the week, you're going to want to get that and download that or whatever. They have changed a little bit the way that things work. I don't know what the school did, but they bought some more Canvas stuff or something like that. So I usually double click on that until it gets down into my little download thing. And that's going to be the best version if I'm printing. But this is all of the notes for the entire unit, at least now. There may be supplemental worksheets or something like that that I think we need to fill in. But basically, that is the way it's done. For you, this last sheet, usually the last sheet I put on there is stuff that we kind of peel off first. So that last sheet is a resource sheet. If you don't want to staple that, you can keep that with your periodic table. And that would be awesome. You'll want that for your periodic table. All right. So if you've got that downloaded, I would change the name to maybe your last name bonding unit. And then basically, I've already taken attendance. So if you don't want to listen to me anymore, you're already tired of it, or you want to talk to your counselor about changing, Mr. Goldstern, Morgenstern, Morning Star, right? Is that what that means?
I think, yeah.
By all means, you can come onto here and watch this video, and it will tell you everything that we are going to do in here today. This video is about 20 minutes long. I'm going to try to do it in 15. We'll see who wins. Right here, you can see there's supplemental help if you need it. This is not one that I normally use, but I really like the way that they kind of went through it a little more step-by-step-y than a lot of the other things. And then if you're like, yeah, I'm digging this, by all means, you can go and do Tuesday's work too, where we talk about multiple bonds and non-unique atom conflict. And you can watch this video, which is, I did that one in 13, and then watch this one. And then, you know, if you're still not done with the chemistry for the week, you can go through and learn about resonance and isomers. And you can basically beat us to Wednesday. So that whenever, you know, you get on here or whatever, you can mute me or do whatever it is you do and act like you're there. It's perfectly fine to me. Just remember that the quizzes and stuff like that are what are graded. These homework things are for practice. I don't try to take up the entire class with just lecturing to you. Try to give you time to do that. You'll notice that after that, it does go backward. So those are the only 3 lessons you can get to Wednesday, and that is it. But it goes backward to an interesting one because this is the electron box configuration thing. That's one that you will need to know for this unit. So if your box configuration stuff is weak, you're going to be a little weakened for this unit. Hopefully that gave you guys enough time to print that out if you're a printer, or if you're not a printer, to at least get it downloaded to somewhere. Let's take a look at this whole bonding thing. The way I've set these up is I've got all the state standards, which is what the state requires me to teach you. I took that and put that into what's called standard-based objectives, which are I can or I know statements, so that you can sit here and say, I can do this state standard, that type of thing. The first part of this unit is review. And if I go too fast, by all means, just, you can always interrupt me. One thing I don't ever pay attention to is the chat thing. So if you send me some type of chat on there, I probably won't see it. Does everybody have thumbs up if you've got the actual, this is like sodium chloride? Claudia, is that working? You're the only one with a picture on. She's already got it.
Sorry?
The notes are showing?
Yeah.
Okay, cool. Yep. All right. So if we take a look, valence electrons, hopefully you know these as the outermost electrons. In order to find the valence electrons very quickly of something, you have to have the periodic table out. If I want to find it for oxygen, I need to know Roman numerals. VI is 6. That's telling me that oxygen has 6 valence electrons. If I did not know that VI was 6. I could write out the entire electron configuration for it. And the last level would be 2s2, 2p4. 4 plus 2 is 6. There's many ways to do it, and that's the beauty of chemistry, and that's the beauty of the periodic table. They all work together for this. So those are valence electrons. Electrons pair onto elements or atoms in what we call the octet, or 8 usually. They like to gain or lose electrons to form 8, or share electrons to get 8. Hydrogen is an exception. Hydrogen only has the 1s sublevel, and the 1s only has 1 orbital, which can only hold 2 electrons. So hydrogen's octet is actually done by 2. Two electrons makes it an octet. All right. So way back, the first week in August, actually it might have been July this year. Way back then, we actually did ionic bonding. Basically, you have a metal. Let's pick for fun. Let's pick a copper 1 ion. Actually, no, let's just do normal. All right, so we'll go with calcium. So we have calcium. Calcium has 2 valence electrons. So if we're doing a Lewis dot structure, we would have 1 electron, 2 electrons. I'm going to make those as X's because I want to be sure that I understand that these electrons belong to the calcium. And with that calcium, we are going to have a chloride. Well, it's actually going to be a chlorine to start with. 1, 2, 3, 4, 5, 6, and 7. Because chlorine is in group 7A. So in order to fulfill the octet rule, this chlorine will need to grab an electron. Well, if we look at the chlorine's electronegativity, it is 3.0. Remember, electronegativity is how attractive you are to pulling an electron towards your nucleus. If we look at calcium all the way over here, its ionization energy is going to be quite low. The first ionization energy, if you recall, is the ionization energy to remove 1 electron. So this chlorine is going to pull an electron off of the calcium, making a chloride ion. Since it has 1 extra electron, it has a -1 charge. Well, it's very unlikely that you would find 1 chlorine atom just poking around. It's more than likely going to be with other chlorine atoms. So another chlorine atom with only 7 valence electrons is going to have the electronegativity to pull that other electron off of the calcium. And it's going to end up with a -1 charge, becoming a chloride ion as well. Well, the calcium is then going to have lost 2 valence electrons, and it's going to get a 2+ charge. That's how ionic bonding works. Basically, you get this type of pattern repeating, chlorine, calcium, chlorine, repeating over and over and over again of all these atoms. That's called a crystal lattice structure. And it is very ionic to see that. It forms when metals form cations and nonmetals form anions. They come together so that they have a electrically neutral crystal lattice. Since it's crystalline at room temperature, they're usually what we call solid then. I can't think of any that aren't, but you can probably find something on the internet and be like, he doesn't know this, that's fine. Tell me about it. I'd be interested to be next time and be like, well, actually, 1 ionic compound is not crystalline. By all means, find it and tell me. Since they are solid at room temperature, because of these electrostatic forces being so strong, they have a very high melting point. It'd be very difficult to take salt and actually melt it on your kitchen, in your kitchen. You'd have to get your, upwards of 800 degrees Celsius, I believe. I believe that's the melting point. It's between 600 and 800 for sodium chloride. The smallest amount of this crystal lattice you could get would be 1 formula unit, which would be impossible to actually get. Like, it would be a feat of miracle or whatnot to get just 1 NaNCl. You're more likely going to get these crystalline sheets of it. But the smallest unit of that would be known as a formula unit. And that's always our formula. For example, the formula above was CaCl2. We know that as calcium chloride. Our major focus for this unit is going to be on molecular compounds. Molecular compounds, for example, like dihydrogen monoxide. They play the game a little bit differently. If we take a look at dihydrogen monoxide, we have H2O. Instead of transferring electrons, they share electrons. So just for fun, those are the boxes representing H's electron box diagram. So those would be 1s's. And I'm going to zoom in a little bit. I'm going to put the electrons in there. I'm going to give them negative spin to start with. And if we take a look up here, here's oxygen, just to make sure we're all on the same page. We have 2s2, 2p, 1, 2, 3, 4, right? So I'm going to put that over here. 2s, 2p. 2s2, 2p1, 2, 3, 4. Just for fun, I'm going to put the 2s up here. And right down here, I'm going to put that first 2p. These other two are going to represent the other 2p's. So if we look at these 2p's, we only have 1 electron in each of them. Each hydrogen only has 1 electron in each of its orbitals as well. So what's going to happen with this oxygen is that those hydrogens are going to share the electrons that are alone in each of these orbitals. That's going to give each hydrogen 2 electrons, and it's going to give this oxygen 2, 4, 6, 8 electrons. Now, you've probably never seen it this way because I've never seen it this way. Today I decided to draw it this way. I thought it might be maybe it looks cool or whatnot. But let's take a look at what this is. These are being shared between the hydrogen and the oxygen. These are lone pairs to just the oxygen. Now, even on Bill Nye, I have seen this written this way because it was broadcast by Disney, and he basically turned it into a big old Mickey Mouse hat, which didn't make sense to me because, you know, the hydrogens were smaller. But anyway, so if we take a look here, what this is showing is 2 electrons paired between the hydrogen and oxygen there and the hydrogen and oxygen there. What's not being shown is the lone pair electrons that are still on this oxygen. And those would be right there. So here we have the 1s from the hydrogen and the 2p from the oxygen. Here we have the 1s from the hydrogen and the 2p from the oxygen. Here we have the 2s from the oxygen, and here we have one of the 2p orbitals from the hydrogen. All of it makes sense. Everybody 2, 4, 6, 8. Oxygen has 8 around it, and the hydrogen each have 2. That's the basis of it. What's the state of matter of H2O at room temperature? Hardest question of the day. Nice, liquid. Who said that? Was it Jonah?
Akshay.
Nice. Liquid. So if we take a look, here is H2O, and at room temperature, it is a liquid. Well, what about this guy? CO2, carbon dioxide. What's its state of matter at room
Yes.
temperature? Gas. Nice. And does anybody know what this guy is?
Solid?
What is it?
A silicon dioxide?
And what's the common name for it?
Oh.
This is sand or glass. Silicon dioxide is solid at room temperature. So if we take a look, all of these are doing the sharing of electrons, making liquid, solid, and gas. They can be any state of matter at room temperature. I just chose 3, but I mean, you could choose sucrose, sugar, that's a solid, right? Or ammonia, that's a gas. Or alcohol, which is a liquid, right? You could choose any of those. Alcohol doesn't necessarily, you need to make sure you keep the alcohol tapped. It will vaporize very quickly, but our vaporization point is higher than that. So, boom, boom, boom. There's the comparison between ionic compounds and molecular compounds. Typically a low melting point. It all depends on their interactions with each other. And we know the naming, hopefully, of that. Carbon, 2 oxygens, dioxide, silicon, 2 oxygens, dioxide, 2 hydrogen, dihydrogen, 1 oxygen, monoxide. Questions so far? We are almost done. Today's an easy day. If you kept up with all that, you are in good shape. So today we wanted to basically get you to learn how to draw basic Lewis structures. So basically to do that, you need to determine the total number of valence electrons. You need to determine the number of bonds in the molecule, draw the Lewis structure of a neutral molecule, and we will be doing that. That's where we'll be stopping today. So let's figure out how to figure out the number of valence electrons. Let's say we have pH3, which is phosphorus trihydride, right? Phosphorus trihydride. P has 5 valence electrons. You could have also done that by looking here, looking at the entire electron configuration, probably a little bit longer for that. Each of the hydrogens have 1 for a total of 3. That equals 8. Well, you saw me draw 3 of them. Anybody want to take a guess at who's going in the center of this? Is it a P or one of the H's?
E?
Why? Why would you say that?
Isn't it like because it's more electronegative?
Oh, you know, fancy terms for it. It's actually, you want the opposite. You want the least electronegative. But hydrogen can never go in the middle.
Yeah.
Think about it one more time. Why would hydrogen definitely not go in the middle?
Because they can only have 1 bond.
That's the key thing right here, right? So with pH3, P has to go in the middle because hydrogen can have only 1 bond. So if you put a hydrogen in the middle, all it would do is bond to another hydrogen and you're done. It can't do anything else. So I'm going to just put P in the middle and then I'm going to attach some hydrogens to it. Now remember, each of these is 2 electrons being shared between each atom involved. We only have 8 electrons total to deal with. So this has 2, 4, 6 electrons already being shown. So that means I've got to put 2 more electrons somewhere in this particular Lewis structure. Well, the hydrogens are all filled up. But if we try to do the octet for the phosphorus, we get 2, 4, 6. That means the phosphorus needs 2 more. Now, I always jump the gun, and I don't like writing dots very much. But where's my whiteout? Nervous. You could also draw that line as 2 dots. Give me 1 second. Worst whiteout ever. There we go. So you could also draw that as that. Either one would be fun. Some people like to do the dots on the central atom in the beginning. It's not a bad habit to take. I just never, you know, I'm just like, nah, I'm a little more messy than most. So can anybody tell me how many valence electrons total NH3 has? It's a race to the periodic tables. Go, go, go.
8.
8. How many does nitrogen have?
5.
5. And each hydrogen has, come here, you. 1. 8 is correct. How about PCl3? Actually, I can't answer. So that means that somebody else is going to do it if they want this class to be any shorter. Is there a way I can permanently mute you, actually? Tell you the truth, I don't even know. I haven't even done it in my head. Oh, I just did it in my head. You can show fingers. I'll even open the chat bar for you if you're so afraid to speak.
Is it 7?
Not 7. PCl3. Oh, look at him. He's getting nervous. He's going to turn on his camera and he's going to show his fingers. He's going to try to hint to you guys. Doesn't want the class to wait that long. No. Amari with 26. Let's see if she's right. So here we have Cl. We have 7 for each Cl. There are 3, so that's a total of 21. For the P, well, we've already done that one. It's V, so that is 5, and 5 plus 21 is 26. Very good. Who's going in the center there?
P.
Why?
Because Cl can only have 1 bond.
Oh, really? I think chlorate and perchlorate would care to argue with you on that.
Oh yeah, but
Anybody else want to figure out why P might? Well, tell me who's going in the center here.
N.
N. Who's going here?
S.
And here we don't really have a center. Anybody give me a rule from just what we've seen? The P in the middle here, the N in the middle here, the S in the middle here, the P in the middle here.
Is it the element that there's only one of?
Yes, that is the first rule. If you look through and you find an element that there's only one of, that element is most likely going to be in the center for what we're doing. So P would be in the center there. And then we would have 3 Cl's around it. Here we have 2, 4, 6. So out of our 26, we have 20 left. Does P have an octet? 2, 4.
No.
So we need 2 more for the P. So there's 2 from our 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And again, I used lines. You could use dots, but that's a lot of dots. Some people hate lines because of Cl, and then a line looks a little weird to them. I don't care. Everything looks a little weird to me. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's how much Amari told us, and that's right. That is PCl3. If we were to look at that, it would look like this. This little hole at the top would be where that lone pair is. Now I will tell you that the angle that I've drawn it here is kind of like this, right? So you don't get to really see that coolness of it or whatever, like how it kind of like raises up off of there. Just like if we were to draw for example, hopefully that doesn't make anybody sick. If we were to draw water, some people will sit there and go, oh, okay, H2O. And they will draw water like that. That's fine, that's water, but it looks like this. You notice whenever I drew the water before I actually put that angle in there, as you get better at it, you will sit there and say, oh, okay, H2O, you know, it's not flat. When we're drawing on paper, all we can do is kind of draw them flat. For tomorrow, I would like for you to finish page 5. And then on page 13, I would like for you to do 1. As always, I will stay on here for the rest of the time. And if anybody wants to see an extra one, I would be more than willing to do an extra one for you. But I don't like to hold, like I said, I don't try to sit here and hold you to the whole time. I've shortened these lessons to basically be pretty concise. So does anybody want to see another one? If you don't, let's just do this. If you don't want to see another one, we'll see you later. Have a great day. Remember page 5 and number 1 on page 13. If you're sticking around, we'll go ahead and do this one real quick. CCl4. So who's going in the center?
C.
C.
It's correct. So then we're going to put these Cl4s all around it. Then I'm going to go ahead. This is what we call the skeletal structure. It's just the basic setup. So I'm going to go ahead and there are 4 for carbon plus 4 times 7, which is 28 for the chlorine. Again, if you don't know where I'm getting that, I'm just looking at a periodic table. There's no other way other than memorization to do this if I'm not willing to look at the periodic table. And chlorine is 7. So that gives me 32 total. So whenever I do this with the C in the middle, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So there is C in the middle. The C has an octet, and each of these Cl's now has an octet. The total number of electrons when we add these up is 32. How many electrons did I use in my Lewis structure? 32. Yes, it is the same number as A. Now, if we were to draw this one out, you can see it looks very flat here. Let's take a look at what it looks like with my models. And I probably should have told them this, but you guys may want to get like some toothpicks and like some like wadded up balls of paper of different size, or I don't want you guys to have to go out and buy like styrofoam and stuff like that. But maybe just like some toothpicks and tell your parents that your chemistry class requires that you have gummy bears, right? So you could stick toothpicks in gummy bears. They're not the best. Like the cheaper candies, like you guys know what grandma has that's like, it's like a gumdrop and it's like disgusting, but like you're like, yeah, I'll eat your candy, grandma. Yeah, like those type of cheap things are usually harder. But what that'll do is if you take a look here, the structure, basically it's looking at it like this. It's a very weird angle and it looks flat with the paper. But let me show you what this actually looks like. So if we take a look, it kind of is that as good as I can get it? I think that might be as good as I can get it. It's got this thing where any way you turn it, it always has the same thing. It's always sticking up. The shape of this is called a tetrahedral. It's quite nice. That's a tetrahedral. It has 4 bonds and 0 unshared pairs. You guys are getting a little extra teaching here. If we take away one of these atoms, that would be like our PCl3. It has 3 bonds, and up here is that 1 unshared pair. So that's the shape of it. It just doesn't have that 1 extra thing sticking off the top. It has a pair of electrons up there that are very close to that atom. And then if we do one more, you can see we get that water that we started with. It has 2 bonded atoms and 2 unshared pairs. That's called bent. That's called trigonopyramidal. And this is called tetrahedral. And that's Thursday's lesson. But you guys got a little extra today. That's all I've got, unless you guys have questions. Bye.
Have a good day.
Hey, you too.
Have a good day. Thank you.
Hey, thank you, Mark, for answering 26. Awesome.
I have a quick question.
Yeah, Brody.
When you say like page 5, does that mean that that's our homework for tomorrow? We should do that tonight?
Yeah. So you should complete page 5 down here. And basically it's just one question now. And then page 13, these 4 problems. You don't submit them to me, you just complete them. They stay in your notebook.
Okay.
Yeah, is that the part of the question?
Yeah, yeah. And
Anything
then-
you submit to me, it will be its own assignment thing, and it'll say this needs to be turned in. It will be pretty clear.
okay. Now,
Yeah.
I just have a quick question. It's like is this like it's a little different from like on my last chemistry teacher, like the things you did, like when you did this like bonding up here, there's like exercise. Like how did you know these lines like had 2 to begin with?
Okay, so back when we started off, right here, we mentioned that each, let me see if I can get it. So do you remember when we did H2O?
Yeah.
I showed you these box diagrams, and each box can hold max, each orbital can hold 2 electrons, right?
Mm-hmm.
That's representing the shared electrons between the oxygen and the hydrogen, and that's 2 electrons. So that's whenever I stated that each of these lines has 2 electrons. Now, if you want, I will tell you that this is set up so that you can read it as well. Usually during the lessons or whatever, I don't go through here and read, but it will sit there and tell you either a straight line or a pair of dots can be used to represent a pair of electrons. A pair of electrons shared between 2 atoms is referred to a bond or a bonding pair. And a pair of atoms that is on 1 electron only is known as an unshared or lone.
Okay. And then my last question is what is this octet rule?
So if you recall, whenever we did the basically the matching up for these things, right? We had to make the charges chemically balanced. So if we had iron 3 and chlorine, for every 1 iron, how many chlorine would we need?
3.
3, yep. So that would be FeCl3. Well, basically that allowed everything to fulfill the octet rule, because chlorine, if we take a look at our periodic table, chlorine has 2, 3, 4, 5, 6, 7 electrons in its valence electron shell. So it is in group 3s2, 3p, 5. So it wants to gain 1 electron. By gaining that 1 electron, it gets a negative charge, and it gets 8 in that outer energy ring. Let me see if I can explain it a different way for you. Do you remember how in 6th, 7th, or 8th grade, if we were to draw the fluorine ion, we have 9 protons in the center? The first energy shell can hold how many?
2.
2. And the next energy shell can hold,
Is it 6?
tell you 8,
Oh, 8.
right? So if we take a look, fluorine would have 2 in the first energy shell and 7 in the second one. If that fluorine were to make an ion, it would gain 1 electron. And when it gains 1 electron, that fulfills that octet. So octet is basically referring to the 8. But in reality, if we look at hydrogen, Hydrogen only has one electron in that first energy ring, but we know that that first energy ring can hold two. So if hydrogen becomes hydride, it fulfills an octet with two. Now again, if hydrogen and fluorine were instead sharing electrons, I should have made that closer. Here we have the 9 positive charges of the fluorine. Here we have its first ring, which will hold 2, and its next ring, which will hold 7. Now, if the hydrogen and the fluorine are sharing this last ring, then this hydrogen would have that 1 electron there. So that means that they're kind of sharing electrons, and basically they would be sharing 2 electrons, which would be that 1 bond. But the octet rule is basically saying you're filling up the electron shell that you're at. Here we have 7, so it wants to get 1 to fill up. Here we have 1 electron, so it wants to get 2. Now I know that 2 is not oct, but that first energy level fills up with 2. That's the game you're playing with them.
Oh, okay. Thanks.
You sure?
Yeah.
When in doubt, what I would do is I would take a look at this one right here, because this is like one of the examples we didn't do. Check through there and make sure that you actually read through it, and it'll tell you, it'll redescribe what that octet is and stuff like that.